formula for the inverse, I shouldn't have erased it. This thing in the denominator is called a determinant. So determinant, written as like an absolute value symbol to a matrix, or sometimes people write it as DT. Both are widely accepted, and I even use both in some cases. And this is by definition this thing AD minus BC. Now, since I talked about the fact that matrices correspond to transformations on R2, I'm at a much better position to explain what this is in a geometrical setting. So you probably have seen this, especially because in multivariable calculus, when you do the cross product, you have to do the determinant, right? So you probably have seen this before, but you probably never have known why this comes up in so many different places. So let me try to explain this. So if you have the corresponding, so let's say you have ABCD, matrix ABCD, and think about the corresponding transformation, which is AX plus BY, CX plus DY, right? That's the linear transformation that corresponds to ABCD. And then let's think about the image of the point 1, 0. What's the image of 1, 0?
It's on the x-axis.
No, x is 1 and b is y is 0, right? So what do you get? A times 1 plus 0. Okay, and then what?
C.
Just C. Yeah, AC. So that's why you get. And then what about f of 0, 1? BD. Okay. Linear transformations, well, I made it sound like you're taking points to points, but what's really going on is you're taking vectors to vectors. So this vector 1, 0 is sent to A, C. Let's just say this is like this vector A, C. And then 0, 1, this vector here, gets sent to, say, another vector here, B, D. Now I'm just assuming that these are some random numbers. I have no idea what these are, but let's say it's some number here, it gives you some vector here and some vector there. Okay. Then there's a question that we can ask, which is, what's the area of this parallelogram? You can think about that. Okay. So let's see. This is A, C, and this B, D. This would be B right here. This would be, oh, no, that's not right. That's not B. This is B. This is, what's this point? Oh, is it too hard? It's vector addition, right?
A plus B and C plus D.
Yeah, A plus B, comma, C plus D. Oh, but, okay. Let's just do this. I think this is easier. So I want to find this area and I'll double it. Then it will be the entire area, okay? Okay, so that's not too bad. There will be like, we just have to subtract 3 triangles from this big one. So this is A, and this point is the y-coordinate of this point, right? So it's D. So this is what we want to do. We want to do this minus this minus this minus this, right? And then this big one will be AD. Okay. Now what about this one? Well, this is A, that's C, so it's 1/2 A times C. Okay? What about this one? This height is D and this side is B, so, oh, sorry, I put it in the wrong place. This is 1/2 AC, okay? C, and this one would be 1/2 BD. Okay? And then, this is a tricky one, but let's see. This is, because this length is D and that's C, this length will be D minus C. And this coordinate is A and this coordinate is B, so this length will be A minus B. So this one will be 1/2 of A minus B times D minus C. Okay, so let's take some time to calculate that part. I'll just delete this one. And you know what, because the 1/2 is annoying, let's just double this, because after all, we're trying to find the entire area, right? So what we have is 2AD minus BD minus A minus B times D minus C minus AC, which is 2AD minus BD minus, we just have to FOIL, right? AD minus AC minus BD plus BC minus AC. That's 2AD minus BD minus AD plus AC plus BD minus BC minus AC. Okay, now some things are going to cancel. I see a minus BD and plus BD, right? I see plus AC and minus AC. And then 2AD minus AD is AD, and there's a minus BC, right? Okay, so what does that mean? That means if you have area 1, because this is the unit square, right? So it's 1, 0 and 1, 0 here. You start with this square, and you apply the transformation F, which is this one. It gives you some crooked kind of a parallelogram. So what happens is that you can take every point in this square, apply F, and the image will be it will end up being some kind of a parallelogram. Okay? And the area of the parallelogram would be AD minus BC. That's what it means. Right? You get that? So the determinant, and this is actually true for any other shape. So let's say you have a circle of radius 1. What's the area? It's pi, right? Then you can apply this F, and it's going to become some crooked circle, some kind of ellipse, right? It's something like this, right? What's the area of this ellipse? It will be AD minus BC times pi. So the geometric meaning of the determinant is that the determinant gives you how much the area has changed under this given transformation. That's what it means. Now, I want you to ask, what's the shape of the output So here's a question. If AD minus BC is 0, then what is the shape of the output of F when this is plugged in? What's the image of the square when you apply F if AD minus BC is 0? Yes?
Would it still be itself, the same image?
No. This is in what proportion the area changed. So the image is what area? What will be the area?
The inside of the image? Which is the square right now?
No, okay, so maybe I should just give you a definite number. So give me 4 numbers that would make this 0. Say 1, 2, and then 2, 4. How's that? 80, okay. So if you have this one, and if you apply this formula to this one, what would you get? You get another shape, right? What kind of shape would it be? Well, the area of that shape we know. What is it? Oh, I thought I explained what this means. What's the meaning of determinant again? What proportion the area changes. It's not the area of the image, but it's the proportion of the area change. So if the original area was 1, then the image will have determinant times 1 as its area. If the original area was pi, the image will have AD minus BC times pi. Okay? That's the meaning of the determinant. So, given that, what is the shape of the well, not shape. What's the area of the output? 0. That's what we know, right? Yeah, it's 0. Okay, what kind of shape can it be? Point or a line. It's either one of those two. Okay? So if AD minus BC is 0, then the image of this will either be a line, or a line segment actually, or just a point, in which case will be the origin. It will be just this. Okay? Now that immediately says, can such a function be 1-to-1? You know? Can such a function be 1? Do you know what 1-to-1 is? What's a 1-to-1? What does it mean to be a what does it mean for a function to be 1-to-1? If you have different inputs, then the output must be different as well. That's 1-to-1. Okay? Why do we like 1-to-1? No. Only when it's 1-to-1 we can have inverse functions. I thought you guys knew this. If you don't have 1-to-1, you can't have an inverse. You know how I explain the inverse function to my calculus students? I recently developed this and it's working well. So I explain, what's an inverse function? And say, oh, it's something that switches input and output. And this is imagery that you should have. Let's say you have a factory, a function that takes in a chicken, real live chicken, and makes it into a chicken nugget. All right? Then what does the inverse function do? It takes a chicken nugget and brings you back into a chicken. Okay? That's what inverse function is. Now here's the problem. There's a farm that has a red chicken and a blue chicken. All right? Goes into the factory, gives you the same chicken nugget. Can you make the inverse factory? No. What's the problem here? Because you don't know whether to make this chicken nugget into a red chicken or a blue chicken. Okay? So it's very important that if you want an inverse function, you better have different inputs giving you different outputs. Okay? You have 1-to-1, not 2-to-1 or 3-to-1. Then you're in trouble. Okay? So now here's a question. this entire square became this line segment. Can it be 1 to 1? No way, because that means that this is somewhat zapped, okay, into this single line segment. So that's why in such a case, that if AD minus BC is 0, you cannot have an inverse. And that's exactly what you see in the formula as well. If you look at the formula for the inverse function, ABCD, you get 1 over AD minus BC of DA negative B negative C. And look at this. If this is 0, what happens? The inverse cannot be defined. This cannot be defined if that happens. Okay? And that has a geometric reason why.